The second special case, when we do have polytropic process. In this polytropic process, we do have BV to the power n is constant. This is the relation between pressure and the volume. So we can just, if we do have a gas, let's say, undergo a change or process from initial state up to final state 2. So BV to the power n is constant. So we can say B1 to the power n is the same as B2 V2 to the power n. And actually this equation can be applied because in some cases it may give you actually pressure and the volume at the initial state, pressure and the volume at the final state, and from this relation you can calculate the value of n. You should be able to do this. In this case, we do have BV to the power n is constant. Just we can take the pressure as function of volume, and we can do the integration boundary work equal to integration of BdV. So at the end, you can get B2 V2 minus B1 V1 divided by 1 minus n. This is the value of the boundary work in case if we do have a polytropic process. This n is called the polytropic index. In case if we do have ideal gas, in this case, we do have BV is equal to MRT, so the boundary work will equal to MR multiplied by T2 minus T1 divided by 1 minus n. And this is the second special case. The third special case, when we do have an isothermal process, we do have a working fluid in a piston cylinder device undergo an isothermal process, so the temperature is constant. So for a gas, we do have BV equal to what? MRT. If it is isothermal, temperature is constant. R is the gas constant, which is constant also. Mass is constant as we do have a closed system. So in this case, BV will equal to constant. So for isothermal process, BV will equal to constant in this case. So we can say B1 V1 is the same as B2 V2. So in some cases, if pressure and the volume at the initial state are given, V2 is given, so in this case we can get the final pressure, or we can calculate the final volume. In this case, if you put this pressure as function of volume from this equation, we can calculate the boundary work for isothermal process. We're equal to, in this case, we're equal to constant, which is BV. BV is constant, so it is B1 V1 or B2 V2 multiplied by ln V2 over V1. V1 is the same as B2 V2, and the V2 over V1 is the same as B1 over B2 also. Okay. In case of ideal gas, BV equal to MRT, so the equation will equal to MRT1 multiplied by ln V2 over V1. And this is a special case when we do have a gas in a piston cylinder device, gas or any fluid in a piston cylinder device, and the process is isothermal. We can calculate also the boundary work. We do have another case, when we do have a gas, also gas, any fluid, not a gas. So we do have a gas or anything in a piston cylinder device, and the piston movement is controlled by a force that is coming from linear spring. So we do have a force that is coming from linear spring, and we do have a gas inside undergo a heating process or cooling process or any other process. In this case, usually at the initial state, this spring is not touching the piston, like the example in the slide number 10. On the slide of chapter 4, you can find this slide. You can find the link for this slide of chapter 4 just in the first comment to just below this video. So in this case, if you look at the slide number 10, we do have a piston cylinder device. Its movement is controlled by a spring. So this is a linear spring. So in this case, at the initial state, we don't have any action of this spring on the fluid inside because it is just touching the spring. So as you add heat, in this case, pressure will be increasing. So the rise in pressure, let's say this is the piston. So the rise in this pressure, delta V multiplied by area, which is the pressure force, will be resisted by the linear spring force, which is equal to force multiplied by the moved distance x. So if this piston is moving a distance x, so this will be the balance. So we can say the change of pressure between the initial state and the final state, B2 minus B1 will equal to what? Delta B will equal to F x divided by area. F is actually, no, the linear spring force is equal to Kx, which is a spring constant K multiplied by x, so this is K multiplied by x. K should be given, which is a spring constant. X is the moved distance and A is the cross-sectional area of this piston. X is the moved distance is equal to the change of volume divided by area. Change of volume, which is V2 minus V1 divided by the cross-sectional area. So from this relation, you can look at the example in slide number 10. You can calculate the final pressure of B2. And in this case, the pressure inside the tank, as this is actually a linear spring, so the change of pressure is linear function of x, as K is constant and the area also is constant, so the change of pressure is linear function of x. And volume is linear function of x, so this means the pressure is linear function of volume. So if you represent this process on the PV diagram, the pressure will be just increasing linearly from state number 1 up to state number 2. And work is equal to integration of VdV, which is represented by the area under this curve. So the area under this curve represents the boundary work. So I think you can get actually the area under a linear curve. In this case, it will equal to half multiplied by B1 plus B2 multiplied by V2 minus V1, and you can see this from the example. And this is another case, just an idea to get the relation, to calculate the boundary work and to get the relation between pressure and the change of volume. But get back to the first law of thermodynamic equation. We said for a closed system, we said heat transfer Q minus work equal to delta U. We have considered this term, heat transfer. We have considered this term work, which is work any other kind of work like electrical work, or if you do have a paddle wheel or something, plus the boundary work. And we have considered the special cases, how to calculate the boundary work when we do have a piston cylinder device and one of the boundaries is moving in this case. Type we are left actually for this chapter to be done with how to calculate delta U. Type, let's consider this.